So we're going to do a little bit of review here, go through all the different hypothesis tests we've had to date, and decide how to set them up, etc. But what I want to do first is remind you that our confidence intervals often, it's not a guarantee, but oftentimes these should match our decisions for our null and alternative hypothesis. So in the case of this one, the difference between two population proportions, if you had a confidence interval between 4% and 11%, what would that say about your null hypothesis? Are you going to fail to reject H naught or reject H naught? What do you think? Well, the important number that's not here is what? 0. Because if 0 was in there, if 0 was a possibility, then 0 equals P1 minus P2. That's the same as, well, move that to the side, P2 equals P1. In other words, you shouldn't be rejecting if that's the case. But notice that 0 is not part of this interval. If you were to actually draw that, then you wouldn't find 0 there. Here, let's add some color to this because it's really cool. There, awesome. So you have 0 here, 0.04, and 0.11. Our confidence interval is here. It doesn't contain that number. So if that's true, that our confidence interval doesn't contain 0, then you should be rejecting H naught. Reject H naught. What about down here in the next one? This one, we have the difference of two population means. So the confidence interval for that difference is between negative 3.67 and 4.53. Again, what's that telling us about your null and alternative hypothesis? Well, so our values go from negative 3.67 to 4.53. What special number is contained in that interval? 0, right? 0 is inside there. So one of the possibilities is that mu1 minus mu2 could equal 0, or mu1 equals mu2. And that is always going to be part of your null hypothesis. So what decision does that correspond to? Fail to reject. Good. Fail to reject. Let's just double check that we actually are recording. Whew. Good deal. All right. So yeah, fail to reject H naught. And I'd appreciate it, even though it might seem like a lot, write the H naught there. Fail to reject H naught. Now with standard deviations are a little bit different because of the way you do the test. In this case, the magic number that you're looking for to try and decide, well, should I fail to reject or should I reject? The magic number is 1. And the reason for that is because if the number 1 is here, if sigma 1 could equal sigma, or sigma 1 divided by sigma 2 was equal to 1, let's make that a little bit better, then that's equivalent to the possibility that sigma 1 equals sigma 2. In other words, multiply both sides by sigma 2. This is part of your null hypothesis. So if this is possible, then you should be concluding HO, that is, failed to reject. Let's look back here. What would the decision be for something like this? Reject. Good. Because 1 is not part of that interval. All right, so fail to reject H naught. Oh, excuse me, reject. Sorry. I was moving on to the next one or two, actually. So fail to reject. So let's get rid of that. There, never happened. Reject H naught. How about down here below? What will we do for this one? Reject. Good. Want to reject this time. If you take a careful look at this interval, negative 3.67 to negative 2.53, the special number that we need here, 0, is not part of that interval. So reject H naught. Now, kind of a funny one because of what coaches do, what football coaches do. But a lot of times, coaches like to ice the kicker, football coaches. And by that, they mean, if it's a critical kickoff or critical field goal in the last couple minutes of the game and the game is close, then they like to call a timeout. So here's some data on whether or not that works. So people were iced the kicker. You had 141 kicks that were made out of 186. And if you didn't call a timeout, then you had 245 kicks made out of 323. The confidence interval for those differences was this. So if your null hypothesis is HO such that probability of making the kick while you're iced is equal to the probability of making a kick when you're not iced, and then of course the alternative is that they're not equal, what do you think you're going to do here? Reject or fail to reject? Fail to reject. Yeah. And if you actually calculated the percentages here, they're different by about 0.1%. They're just so equal. And you can see that in the confidence interval. The confidence interval is almost centered right at 0. The p-values you get would be like 0.995. It's really, really close to 1. It's as far away from rejection as possible. All right, so that's kind of a little warm-up on some of this stuff. Let's actually run through some hypothesis tests. And so the goal here is to set up your null and alternative hypothesis. Your null and alternative hypothesis should contain some very predictable things. Mu, sigma, and p. And then for H naught, you should have less than or equal to, or greater than or equal to. And for HA, less than, not equal to, and greater than. So depending on the problem. Now these are from Triola 11th edition. So just kind of sit back and enjoy the ride, because I don't think you have a copy of this one. Let me start with this one. Problem number 17. Listed below are the body mass indices for recent Miss America winners. Use a 1% significance level to test the claim that recent Miss America winners are from a population with a standard deviation of 1.34, which was the standard deviation of BMI for winners from the 1920s and 30s. Do recent winners appear to have a variation that is different from that of the 1920s and 30s? So there's two things you got to decide, and I would decide them in this order. First of all, how many populations are you dealing with? Secondly, what parameter are you testing? So, first things first, how many populations are we dealing with? Anyone? Make me look good. This is going out on video, all right? Laugh. All right. How many populations are we dealing with? All right, thank you. All right, so one population. And what parameter are we testing? Good, standard deviation. Thank you. So All right. So let's see if we can't write the null and alternative hypothesis. Let me give you a minute, and then I want you to write it. So Prannoy, what that will look like? Okay. Dale, some help? Okay. Ryan? Yeah. So sigma equals 1.34 and sigma is not equal to 1.34. So there's one population, so we only need to list one parameter. Don't necessarily need to subscript that one because it is just one population. So cool. All right. If you did finish running through the test, we get a p-value for this one. Let's see. You know what? I don't have that number handy. Sorry. Oh wait. P-value would be 0.7368. So p equals 0.7368. So what would that tell us about our null hypothesis, Kayla? Yeah, fail to reject. Yeah, good. And then you can look back at what the original claim was and decide how you want to word that conclusion. All right. Thank you both. So anything on this one before I move on to another one? We're going to keep on doing this so we run through all the different tests that we have. Okay. Let me see. Page 470. We're going to do number 17 again. Morality and marriage. A Pew Research Center poll asked randomly selected subjects if they agreed with the statement, "It is morally wrong for married people to have an affair." Among 386 women surveyed, 347 agreed with the statement. Among 359 men surveyed, 305 agreed with the statement. Use a 5% significance level to test a claim that the percentage of women who agree is different than the percentage of men who agree. So, decide how many populations you're working with, decide what parameter you're testing, set up the null and alternative hypothesis. Okay. Stacy, how many populations are we dealing with? 2. Thank you. And what parameter are we testing? Austin? P. Good. Catherine, do you want to give us HO and HA? Perfect. I'll go with that. So H naught, these two parameters are equal, and I like that you subscripted them. All right, it's helpful when you're stuck with doing this stuff either on a calculator or using StatDisk if you subscript these things. So perfect. Two populations, two proportions. Now let's actually do the test. One thing to kind of keep in mind is the wording of this. They say among the 386 women, there were 347 of them that said, yeah, it would be immoral. So you don't have to subtract off anything, etc. It's just going to be the 347 out of the 386. And then likewise for men, let's actually run through and do the test. So let's see here. What we get is a p-value of 0.0415. Now, if we're doing this test at the 5% significance level, what's that telling us about HO? Fail to reject H naught or reject H naught? Reject. All right. What I like about the graphing calculator is that it's going to take the values that I just did there and import them to a two-sample Z interval. So there we go. B, two-sample Z interval. So it's got all of them populated. There's the confidence interval for the difference in men and women who think it's okay to, or find it's not okay to have an affair while married. What important number is either in or out of that interval? 0. So the fact that 0 is not in here, is that consistent with our conclusion to reject H naught? Yes, that's good. Now, confidence intervals don't always, but they almost always match up that way. We did find one earlier this semester. You can look that women seem to have a higher rate of answering this question that yes, it is wrong. Men, well, I guess our morals are a little bit more situation dependent, but let's just stick to the data. All right. Yeah, about 85% as opposed to 90%. Yeah. All right. let's try a different one here. Number 15 on page 440. So okay. So simple random sample of 25 100 millimeter cigarettes is obtained, and out of the 4,000 different chemicals found in cigarette smoke, tar content of each is measured. The sample has a mean of 13.2 milligrams and a standard deviation of 3.7 milligrams. Use a 5% significance level to test a claim that the mean tar content of filtered 100 millimeter cigarettes is less than 21.1 milligrams, which is the mean for unfiltered king-size cigarettes. All right, so I'll give you a chance to work on that. Again, the same kinds of problems or questions we're going to work on here. Set up the null and alternative hypothesis. do you think here? What would the null and alternative hypothesis be? Mm-hmm. Okay, good. Now, what symbol do you use for mean? Mu. Good. So mu is less than 21.1. The null hypothesis would then be mu is greater than or equal to 21.1. Don't be surprised if you look in the book and find out that they don't do the greater than or equal to, they just do equal to. That's fine. I will accept this or this. Either one of them is fine. Now the p-value for this test happens to be a flat line of 0. What's that telling me about my null hypothesis? Fail to reject or reject H naught? Reject H naught. That's a pretty substantial rejection. So in words, there's sufficient evidence to support the claim that filtered 100 millimeter cigarettes have a mean tar amount that is less than 21.1 milligrams. So, okay. Let's continue. Page 484, problem number 25. Many studies have been conducted to test the effects of marijuana use on mental abilities. In one such study, groups of light and heavy users of marijuana in college were tested for memory recall, with the results given below. Use a 1% significance level to test a claim that the population of heavy marijuana users has a lower mean than light users. So, testing you how many items you can recall. And these are the results. Your job is to try and set up the null and alternative hypothesis. There's actually something a little bit more just to pay attention to in this one, but we'll get to that. All right, so let's take a look here. How many items in our population? 2. What parameter are we testing? Mu. All right, so you could do, say, mu sub L equals mu sub H, and then mu sub L. Let's see, do we want different or... Oh, we want to test if heavy marijuana users have a lower mean than light users. So mu sub h is less than mu sub L. And of course, this then would become the greater than or equal to, or you can just leave it as equal to. Either one is fine. Now, if you actually ran out the test, I think you'd find that there is a difference. You've got a p-value of 0.006. So there is a significant difference between the heavy and the low frequency users. How are we looking on that one? Yes, sir. No, go ahead, please. Great question. That was going to be something that I was going to mention here. Are these matched pairs? Is the data somehow dependent, or do you think these scores are independent? Independent, yeah. You know, if somebody's a heavy user, you know, what their recall score is going to be independent of yours. All right. So yeah, independent. Yeah, that is something that you are going to need to spell out for me when there is a possibility. So independent. Let's look at page 495, number 14. Is there anything else on this one? Yes, sir. Did you do a 2-sample t-test? Yeah, but I guess it depends if you put it in as a Z or a T. This needs to be a T. I did it on my graphing calculator. So, I mean, the results might be a little bit different. They should be similar. I got 0031. 0031. Do I have all my data typed in correctly? 53.3, 51.1, 3.6. All right, we'll tell you what. Let's go through and do it then. So let me switch over to here. Let's do analysis, hypothesis testing, mean 2 independent samples, sample size. For the first one was what? 64. Sample mean was 53.3. Sample standard deviation was 3.6. Say again? Oh, the significance level? Thank you. Mean 1 is less than mean 2. So these are the light users. All right, and then for sample 2, we had 65 people with a sample mean of 51.3 and a sample standard deviation of 4.5. Are all those correct? I got that first, but then I changed the way I put the sample. I think what was wrong with that first one was we had the we had the sample one, the alternative mixed up. So remember, we're trying to test whether or not heavy users have a mean that's less than light users. So let's take a quick look at the data again. So heavy users, that's what I put in. Let's see, these are light users. So that's our population 1 in StatDisk. So population 1 is greater than population 2. That would be, that doesn't look right. Let's look back here. So this is population 1. This is population 2. So if the alternative hypothesis is true, then, oh yeah, okay, we're okay. So mu sub L and mu sub H, then we should see that mu sub L is greater than mu sub H. In other words, population 1 is greater than population 2. And I think that's what we have here in statistics, right? Mu sub 1 is greater than mu sub 2. The light users have better performance than the heavy users. So yeah, we're getting a different p-value. What that might reflect is the way our calculator calculates the degrees of freedom as opposed to the way statistics is calculating the degrees of freedom. In a test like this, the degrees of freedom aren't exact. So you have to use some kind of an approximation. So depending on what approximation they use, they might have a different value. It doesn't really affect our conclusion though, does it? Because both of them are substantially lower than 0.05 or 0.01. All right. Take a look at the confidence intervals. The confidence interval telling us the same thing that our hypothesis tested. Doesn't have 0, right? So it's telling us again to reject H0 because 0 is not one of those possibilities. Okay, a couple more here. Page 495, number 14. Yes, sir. It'll be the last thing we do. Yeah, type 1 and type 2. Listed below are systolic blood pressure requirement or measurements in millimeters of mercury taken from right and left arms of the same woman. Use a 5% significance level to test for a difference between measurements from the two arms. What do you conclude? So again, set up the null and alternative hypothesis. How many populations do we have? 2. What parameter are we testing? Logan? What parameter are we testing? 14. Well, let's do it by elimination, right? Remember, we've got 3 different choices. We've got mu, sigma, and p. Let's go with the low-hanging fruit first. Are we dealing with a population proportion here? No. Are we talking about the standard deviation? No. So what's left, what has to be left, is that we're talking about the mean, the average. So, good. Set up the null and alternative hypothesis. And then the last thing you have to decide is, are these dependent or independent? All right, so Lauren, what's your null and alternative hypothesis going to look like for this one? Good. Mu over the right equals mu over the left. Right. Or I should say correct, probably. All right. Now, the big question is it dependent or independent? Yeah, it's dependent. If you're measuring the same woman, then, you know, if she's got high blood pressure in one arm, she's going to have high blood pressure in the other arm. Now, there is some kind of a relationship there. Now, you can see that if you're getting your life insurance measured or you're getting your blood pressure taken for your life insurance, try and convince the technician to take it from your right arm. Right? All right? The score is going to look better, but the left arm, I think, is what you're supposed to be doing. In any case, I don't think I really need a statistical test to tell me that there's a difference. Yeah, you're going to have a p-value of 0 on that one. Are we okay, though? The big thing here is that it's a test of 2 hypotheses, or a test of quality of means in the dependent case. That's what we're trying to demonstrate here. Yes, sir. Original claim. Test for a difference between the two measurements. So if there's a difference, that's right here, that they're not equal. All right, let me find the next one. Page 431, number 7. This one's a little bit funny, amusing. There's a book out, a manual on how to write, how to have a number one the easy way. So if you want to write a number one song, there you go. Do it the easy way. A simple random sample of 40 current hit songs results in a mean length of 252.5 seconds. Assume that the standard deviation of the song lengths is 54.5 seconds. Use a 5% significance level to test a claim that the samples from a population of songs with a mean greater than 210 seconds. So basically you're testing whether or not the advice given here is good. Okay, how many populations are being tested here? One population. What parameter? Mean. So you should have mu equal 210 and mu is greater than 210. Bless you. Now, if you're being really sharp on this one, what they're giving you is not S in this. They're actually giving you sigma, which would result in a Z test as opposed to a T test. Well, they tell us about the standard deviation. The standard deviation is 54.5 seconds. The results aren't going to really change that much, so I would just stick with a T test. We did not do the Z test for stuff like this, so you're not going to be quizzed on it on an exam. Page 505, number 16. So some familiar looking data, different problem. Let's see if results are similar. What? Oops, problem number 16. Listed below are the BMI for Miss America winners from two different periods. Use a 5% significance level to test the claim that winners from both time periods have BMI values with the same amount of variation. So we can use a little subscripting to help us out here. How many populations? 2. What parameter? Sigma. All right, so let's see. Lauren. No, I think I picked a new. All right, let me just do this one then. Let's see. We're testing whether or not BMIs have the same level of standard deviation. So that'd be recent winners and past winners have the same level of variation in the BMI. That's going to result in an F test, the F distribution section 9.4 stuff that we just finished working on. Okay, one more and then we'll do type 1 and type 2 errors to wrap things up. So page 421, number 10. Yes, sir. No, I mean, just as long as it's something I can understand. What I don't want is for people, I mean, and I know that the author does it, and that's fine, you know, he's writing a book, whatever, I'm not. I don't want sigma 1 and sigma 2. You know, depending on the problem, it's not really clear what that is. I think it's much more helpful to me and to you to have these things labeled in such a way that they make sense. Yeah, I mean, that's fine. I mean, just as long as I know what it is. You can even write a word there. It doesn't have to necessarily be just a letter. If you look back at what we did earlier, yeah, here it is. I mean, I subscript it with ice and not ice, or ice and no ice. I mean, there's nothing wrong with going beyond just one letter to subscript your stuff. So, yeah, as long as I can tell what's going on, it's fine. Yes, sir. That's fine. So if you had sigma sub p equals sigma sub r and sigma sub p not equal to sigma sub r, sigma sub r, that's the same thing. So I'm not going to worry about that. Angela?
So for like the last 2 questions that we did on the test, we would just have to put like the null and alternative and not, state if it fails or.
Well, all we're doing is we're practicing the setup right now. Because what I found is a lot of people, they can do the work once they get going. It's just setting up, because a lot of times in these problems it's nuanced. I mean, when we did this one about dependent, it really didn't tell us we were working with the mean. It didn't tell us we were working with dependent. So, I mean, if you can work on that, if you can get that, then the rest shouldn't be that bad. All right, so just 2 more, so bear with me if you would. Let's finish them off. Let's see here. It was page 421, number 10. How many populations? 1. What would the null? Charbel, thanks for volunteering. I didn't see you back there. yeah, flipped is better, and the proportion is 43%. All right, so HO proportion equals 43%. HA, it's not equal to 43%. So one population, and the parameter is P. Okay, one last thing before we wrap it up, and that is type 1 and type 2 errors. So let me remind you a bit about those. And I'll try and say it in as simple of terms as I can. A type 1 error, HO is true, but the data reject that claim. But gets rejected. Or you could say the data reject that claim. All right, this is what's true, but our conclusion is this, or we conclude or reject HO is false. For a type 2 error, HO is false, but the data fail to reject that claim. So HO is false, but the data failed to reject that claim. Now, for our last problem then, page 411. Let me just speed things up by giving you the null hypothesis, an alternative hypothesis. The percentage of Americans who believe that life exists only on Earth is equal to about 20%. So percentage of Americans who believe that life exists only on Earth is 20%. So it's going to be HO is at P equals 0.20 and HA such that P is not equal to 0.20. So let's see if we can't figure out what a type 1 and a type 2 error is for this case. Okay. So, does anyone want to give it a shot for the type 1 error? What would a type 1 error be in this case?
Data confirms that the percentage of Americans who believe that life only exists on Earth is equal to 20% when actually it is not
Sounded reversed. Let's see. A type 1 error, we would reject the claim that the percentage of Americans who believe that life exists on Earth is equal to 20% when it actually is 20%. So 20% of Americans think that life only exists on Earth, when in fact, and the data lead to the opposite conclusion. Charbel? Yeah, try yours. No, that's reversed. The data shows that the true proportion, or the data shows that the proportion is not 20%, when in fact it is. So you got to remember, H naught is true. So this is what's true, but the data lead us to this conclusion. Austin?
Can I try mine?
Yeah, go ahead.
Percentage of people who believe life exists on Earth is 20%, although research rejects that claim.
Sure. Percentage of people who believe that life only exists on Earth is 20%, even though the data rejects that claim. So you're saying that this is true, but that's what we conclude. Stacy, is yours more or less the same? Okay, thanks. And let me do type 2 for you so I can get you out of here. Remember, in a type 2 error, that H naught is false, but we can't reject H naught. So in terms of a type 2 error, fail to reject that the percentage of Americans who believe that life exists only on Earth is 20%, when in fact that percentage is different than 20%. So this is what's true, but we conclude this because we fail to reject it. Okay. This is what's true, but we fail to reject this, meaning we're stuck here. We can't get past here to support the alternative hypothesis. All right. So test will be on 8.1 through 9.4. Good luck. See ya.